support vector machine class and so on. Okay. So this is just the equation for the maximum margin separating hyperplane. Again, you don't need to worry about this equation right now. Okay. So what I do is I create a random data set. Okay. I got my features, I got my labels X and Y. I fit an SVM model. Okay, I fit an SVM model, and I am just seeing what my predictions are. Okay. So this is for class one. Maybe this is for class zero. Uh, so can anyone let me know from the yesterday's lecture what these points highlighted in black are called? Actually, what are they called? So I want to know what is the dotted line here? What is this line? What are the dotted lines? What are the points that are circled? Can anyone give me all those terms? Or if can anyone tell me if they didn't understand yesterday's class? So first, what is this line called? This one?
Sir, if you can provide a brief recap, it would be helpful.
Okay, fine. So support vector machine, the idea is to create something called this maximum margin separating hyperplane. Okay. So you have the data set like this. You don't have any of these lines in between. Okay. What I want to do is draw something called the decision boundary. So whatever points are towards this side, below this line, I'll classify it as red. If it's above this line, I'll classify it as blue. Okay. But where do I draw the line? That is the question, right? How many lines can be drawn in this particular space? How many lines can be drawn?
Multiple lines.
Yeah, so it can be infinite number of lines. Okay. So I exactly want to draw a line so that the distance from this set of points and this set of points is maximum. Okay. So this particular distance is called the maximum margin. Okay. Okay. And I want to be exactly in the middle so that the distance from these 2 points is the highest. So I should draw the line in such a way. Okay. And so from which point, that is the next question, right? From which point should I find the maximum margin? So as you can see, like these two and this point, okay, that is more farther from these points, right? So the line should be somewhere between these points in the middle. Okay. So that's why these points are called support vectors. Okay. Is the explanation fine? You don't need to worry about how the line is found. I mean, there is some optimization involved. We won't go into the details of that, but this is the basic concept. You have to find a line that can separate these two classes. That's the ultimate goal here. And make sure that this distance is the maximum. So if I draw a line here, the distance from this point to this line will increase, but this is lesser. You don't want that. You want it to be equal on both sides. So fine.
Yes, sir.
Okay. And what are hyperparameters? Hyperparameter tuning. hyperparameters. Hyperparameters. What are those exactly? So those are some values you change in your model, right? So that you can get the best possible accuracy in this case. So each model has its own set of hyperparameters. For the SVM case, you have the value for C. Okay. You also have to define something called a kernel, and there is the other hyperparameter called gamma. Okay. First, we'll check the influence of the kernel functions. Okay. You have four different choices. Okay. With three different choices. You have the linear kernel, you have the RBF, you have the polynomial kernel. Okay. So hyperparameters, those are your choices so that you have to find the best possible choice for your model. Okay. Let's see if I keep varying all these things. Okay. And again, for this example, I'm using the iris data set. Okay. Let's see how this. Okay. The ones in blue, red, white, this is your decision boundary. Okay. So what do you think? Which among these four do you think is the best? Which among these four do you think is the best? See, relate the concept to this diagram. There are three different classes, three different flower species. So when it's blue throughout this whole thing, so whatever new point comes into this region, it will be classified as blue. If the point lies in this region, it will be classified as white. In this region, it's red. So which among these four do you think has the best possible separation? Just take a guess.
Linear SPC.
Yeah. See, that's good. Because in this decision region, most of the red points are being covered. I mean, there are some white points in this region that are misclassified. Okay. But entire blue is covered. Most of the white is being covered. Most of the red is being covered, and so on. Okay. So maybe the linear kernel is the best possible hyperparameter for this specific data set. Okay. But let's move on to the another data set. Okay. Just give me a minute. I'm having some issue loading the penguins data set, so we'll go ahead with the iris itself. Okay. Yeah, now it's loaded. Okay. So you have 5 features. Okay. And there are some, what does nan means? I mean, the nan value here indicates that you don't have any measurement for the specific features. So if you don't have any measurement for these features, you just drop those rows. That is what df dot drop in is doing. Okay. Doing that, I'm splitting my data set. Why should I split my data set? I explained the pipeline before. What? Why should I split my data set?
For training and testing purpose.
Yeah, training and testing. But why do we need a test set?
So we can
Be-
predict.
See, without even having the test data set, you can predict. Okay, you already have your model with you. So if you see, once you have developed all your ML models, right? So if you want to deploy it in real life, okay, some other new data point comes to you. You want to do predictions. Okay. You want to test whether, and the model has never seen that data point before at all. And you want to check whether it's correct or not. So what you're doing here is exactly that. You want to keep a test set that the model has never seen before, okay, to evaluate its performance properly. Ultimately, you want your ML model to generalize well. Even if the data point is not seen by the model, it should make the correct prediction. That's why you're making this train test split. Okay. Um, let's see. I'm just taking again for visualization purpose. I'm just selecting 2 features. Okay. And if I draw an SVM, this is my line. This is my maximum margin separating hyperplane. Do you think this is good? What do you think? Does this model do classification properly? Is it perfect?
Yes.
I mean, it's not 100% accurate because below this line there are some orange
Few
points.
orange and blue are being overlapped around the
Yeah,
line, but
yeah,
still we have managed to get almost a perfect one.
yes, that is correct. Yes. Okay. But this is the training set. Okay, but we want to move on to the test set and see how it works. See, you got 97% accuracy. That's very good. Very similar performance. Okay. In this case, what I do is I'm doing it for 3 classes. Okay. Did I talk about one hot encoding before? Did I talk about one hot encoding before? Previous classes?
No, sir.
Okay. So why should I do one hot encoding? Let's take the island and gender. Okay. How do I mean these are just numbers that I can directly put it in my model. But think about how do I put these strings in my model? What should I do? I want to include island features and gender features in my model, but I want it as numbers. What should I do in this case? So what you do is, let's say here, male, I'm converting it as 0. I'm putting it as 0, okay? I'm putting it as 0. Female, I'm putting it as 1. Same for island, different island, I'm giving different numbers, 0, 1, 2, 3, 4, or so on. And I'll convert this, I'll put it in my model. But again, there is another problem, major problem here if I use just 0, 1, 2, 3, 4, 5, and 6. What is the problem? Can anyone guess? See, in the case of build depth, okay, 18.7 means, I mean, if it's greater than 17.4 in this case, that means the build depth is higher, okay? But in the case of gender, there is no concept of giving a higher value to male and lower value to female, or the other way around, and so on. Okay. Here, one indicates that there is higher weightage given to female than male. But there is no concept of that, right, in categorical variables. So what you do is something called one-hot encoding. Instead of uh, I'm male 0 and female 1, what I'll do is I'll give it like this. Okay. So 1 from 0. Mhm. So what I'll do is if there are, let's say, 5 different islands, for example, I have 5 different islands, okay? What I'll do is I'll first assign different. So for one island, I'll give it a 0, another one, 2, 3, 4. So I'll assign this and then I'll do something called one-hot encoding. So for the first island, the value will be 1, 0, 0, 0. Okay. For the second island, it will be 0, 1. And this is how I'll represent. Essentially, what I'll be doing is converting this single feature into, if there are just two uh, genders in this case, I'll be keeping two other columns for male, for female. Okay. Then it will be like, if it is a male, it will be once. If it is female, it will be 0 in this column. Similar case for the female column. This is what is one-hot encoding. Any doubts in this? So again, as you will see here, okay, see, I'm doing one-hot encoding. If it is, I've added two more columns. Okay, here there are only two islands, so I've added two more columns in my features. Okay, so if it's one in this column, the penguin is a female. It's not a male, so it's 0. If it's 0 here, it will be 1 here because the penguin is a male. Similar case to islands. If it's living in Bisco, it's 1. If it's in Dream, it's 0. I mean, if it is living in Dream, it's 0. Any doubts till now? Okay. And similarly, I talked about scaling also. Like each feature they have different ranges. Okay. That case, you'll be you want to make sure that every feature has the same range. That is what this standard scalar class does. Okay. And if you see right now, see build depth, it had range till 18, 17, 20, and so on. Right now it's 0.19 minus 0.06. It's between mostly minus 1 to 1. Most of the values right in between these range. Okay. And you have to make sure that you are applying the standard scalar after doing your splitting. Okay. You do fit transform for extrain. Okay. And transform for test. You have to remember that. And moving on to hyperparameter tuning. What is the concept of hyperparameter tuning? Why should we do it? And what's the most simplest method of doing hyperparameter tuning here? Just think about yesterday's class and answer. What is hyperparameter tuning? Anyone? So for SVM, I talked about three hyperparameters. Right? What are those hyperparameters? We saw the influence of one hyperparameter already in this tutorial. What specific thing that we changed in the SVC class? What did we change?
Kernel.
Yeah, kernel is one. So what did we do? What is tuning then? What is hyperparameter tuning? You try different combinations of hyperparameters and come up with the set of hyperparameters that give you the best possible performance, right? So how many hyperparameters did we discuss in SVC? There are three different sets, right? So first thing is grid search. Okay, what does grid search do? I'm defining three different hyperparameters. One is C, one is gamma, and one is kernel. I can write poly. Okay. C, I'm having different values from 0.1, 1, 10, 100,000. Gamma, I can have different values like this. Kernel, I also have two choices. So totally, how many models should I train if I'm using grid search? You have to look at all combinations. So totally, how many models should be there? If you want to look at each and every individual combination, how many models should I train, get the accuracy for? So I have one, two, five values for C. It will be 5 times two value for kernels, 10 and 10 times 5. So 50 different models I have to try. Okay. This is what hyperparameter tuning is. Okay, you have to try all different combinations and see which one gives you best accuracy. So you have the grid search CV class from scikit-learn. Estimator is the model that you want to train. It can be any model. It can be linear, it can be KNN, it can be logistic regression, it can be naive-based classifier, it can be anything. Okay, any estimator. In the parameters dictionary, what you give is the hyperparameters and the corresponding range that you want to try. And also, I talked about cross validation yesterday. So I'm doing five-fold cross validation. Okay, let's see. See, it's quite fast. As I said, 50 candidates, I mean 50 different models you have to train. Okay. And after everything is done, the best possible hyperparameter combination is this one. The value for C should be 1000, gamma should be 0.01, and kernel should be RBF. Okay. Any doubts? And what I'll do is I've got the best, I've got the best classifier here. I've fitted using my training set. I'm doing predictions on my test set and calculating the accuracy score. See, it's 98.8%. In the previous case, what accuracy did I get? 97.6. Not a huge improvement, but there is an improvement, right? 97.6 to 98.8. This is why you have to do hyperparameter tuning. Okay. Any doubts? And again, you can get the classification report, precision recall, F1 score. You can also get the confusion matrix and so on. Okay. See, and if you just want to use naive based classifier, you import it. Okay. This is for the naive based classifier. Okay. Naive based classifier, it's 96.4. Again, you don't have many different hyperparameters to play with here in the naive based case. But if you see a comparison between these two, support vector machine turns out to be the best possible model for this specific data set. In some other data set, naive based can give you better performance. We don't know for sure. Okay. Yeah. Any doubts? Okay. Moving on, as I mentioned in yesterday's class, you can also do regression. Okay. Using support vector machines. So I'm generating a data set here. Okay. A random data set. 4 features, 1 label. This is a regression problem. Okay. And these are your scatter plots. So x1 versus y, x2 versus y, and so on. 4 features versus 1 label. Okay. What I do is do train to split again. I'm fitting a linear regression model initially. Okay. Score is around 0.7. The mean squared error. Mean squared error should be low. Okay. But in this case, if I fit a support vector machine, I'm getting 0.67, which is better than the linear regression model. And this is the for the linear kernel. But if I use RBF kernel, it's 0.61. This is even better. Okay. See, just a single kernel function you change and see how drastically the error is reduced. You should remember for classification, accuracy, FN score, all these should be higher. In the case of regression, mean square error, mean absolute error, it should be lower. You should remember this point. Similarly, I'm doing hyperparameter tuning again. 2 different parameters, C and epsilon. I've got the best estimator. The best value for C is 2, for epsilon is 0.2. Using the RBF kernel. Okay. Here I did not mention that it's the RBF kernel. Okay. So the score is a bit higher, but here you can mention the kernel as RBF. Then, I mean, okay, this is a different scoring. They're using coefficient of determination of scoring. So R2 should be higher. So in that case, this is the best possible model. Any doubts? All right. So the grid search, CV, everything is there. Model selection, there are different methods like Bayesian optimization, random search, so on. But if you have a model that trains faster, you have less combinations of hyperparameters to try, you can go for grid search. That is the idea here. Okay. Any doubts, guys? Okay. I'll share this notebook in a while. And there are no doubts. Thank you for attending. We'll see you tomorrow. Tomorrow we'll be discussing about trees. Okay. That Ritraj will be taking tomorrow's class. No doubts. We can end the session here. Thank you.
Thank you, sir.